Assalamualaikum Adam.
Salam. I just bought this new Zoom account, so we will not be cut off after 40 minutes. Semuanya tengah nak tengok apa benda features dia. Okay, how's everybody today? Are you good?
Alhamdulillah.
So we have
Alhamdulillah, madam.
Munirah, Afiq, Muhammad Anas, Mirza, Ni Azuddin, Azian, Azimuddin, Iqmal. Yang lain? Where's your video? Did you attend the first class? Siti Farhana, nampak anak tudung je. Okay, so the rest of you? So you need to pull down a bit the video, the camera, Farhana. Can you hear me?
Bab.
Yes, Syed.
Yes, madam.
Kenapa ni? Macam mana ni?
Yes, madam.
So mana video Muhaimin, Haris, Amirul Faris, Muhammad Anas, Muhammad Anas ada dua. Syed Zarif and Hazim. Confuskan saya. Mana yang lain ni? What's your video? If you don't tell me why, I will kick you out. You know that, right? That's the rule. If you cannot,
kamera.
Amirul Faris seorang lagi.
Saya ada kamera madam. Kejap nak setting jap.
Oh, ni first class awak dengan saya ke?
Yes madam.
Oh,
Kalau register.
Register. Maybe
yes madam. Free online.
I might change the mind. So
change the mind.
Okay, so okay, let's start the class. Today, so welcome, this is the second week. Unfortunately, for this semester, we only have 11 weeks. So I'm not sure how we're going to complete the 11 weeks, but maybe I will cut off some, as mentioned before, I will cut off some, apa nama tu? Content. So let me see. So let's look at, I haven't discussed the course outline with you, right, before? Hello?
No, madam.
Have I discussed the course outline with you?
Hello.
No, madam.
Okay, so let's go through the course outline. Macam mana nak share ni? Share. Okay, can you see?
Yes madam.
Okay, so these are the learning outcome. Upon completion of this course, the student should be able to bagus Zoom baru ni, dia bunyi ada macam bell kalau ada student enter. Okay. Masalahnya dia akan sentiasa bunyi kalau student datang lambat ataupun internet problem. Okay, students should be able to describe semiconductor physics together with Venn diagrams, electric field, carrier transport for semiconductor material or PN junction at different devices and condition. Okay, so we'll go through the physics, semiconductor physics, what's inside it, how do you get current, and what affects the current inside semiconductor material or PN junction. So we will also learn about PN junction diode with different biases and conditions. Number 2 learning outcome is to describe the working principle of optical devices such as lasers, LED, solar cell and photodetectors. So we also be looking at that, inshallah. By the end of the course, hopefully, if people ask you how a LED works, right, you'll be able to answer. Macam mana saya tengok? Saya kena stop screen sharing kalau nak This L. Saya kena keluar kalau saya nak. Oh, tak boleh. Okay. Afiqah dan Siti Farhana keluar masuk balik. Okay. So, okay. Are you with me?
Yes,
Yes,
madam.
madam.
Okay. So, by end of the course, hopefully you'll be able to explain ni lah laser, LED, solar cell and photodetectors. Because the basic of all four are just PN junction. So if you learn PN junction, and actually your assignment will be on number 2. Number 3, describe BJT working principle and its secondary effect. So we'll be learning about how BJT works, working principle, and what are the things that can affect the BJT performance. And number 4 is just describe the MOSFET operation. You will understand how MOSFET works. The detail of it we won't have time to cover in the course. Okay, so if you look at the weeks, week 1 supposed to be last week, we should review semiconductor fundamentals, basic crystal structure, band structure, doping, transport phenomena, include drift and diffusion. Tak sempat lah kan? Okay, maybe we'll do it today. And then we are supposed to week 2 electronic levels in semiconductor, in crystalline solids and in quantum well, direct and indirect bandgap semiconductor. So you'll be learning about how the electronic levels dipanggil energy state in semiconductor and also in quantum well. You'll be learning what is quantum well as well, and also what is direct and indirect bandgap semiconductor. Then the third week, semiconductor defects, lattice mismatch, structure strain, epitaxy. Week 4, theory of impact ionization, avalanche breakdown, theory of tunneling, scattering rate, insyaAllah. Then week 6, carrier generation and recombination, optical absorption and emission in semiconductor. Pun penting. Week 7 to 8, PN junction theory, energy band diagram in zero bias, forward bias and reverse bias, generation and recombination current. Yang lain tu baca sendiri lah. So I already gave you the course outline, so you can just read. So basically we'll cover all this. Yang mungkin saya cut ialah here dekat week 11 to 12 there are many secondary effects in BJT. There are thermal effect, early effect, avalanche breakdown, current crowding. Mungkin kita buang 1-2 lah. Okay. And definitely tak cover special topic effects of radiation on semiconductor devices. Okay. Any question?
No, so far no.
No, madam.
Alright. So next. Okay, next kita akan go through my slide. Oh, by the way, can you please write down your name and metric number in the chat for attendance. Okay, name and metric number. And also for those who have problem, ada internet problem. Hari tu Nisa ada kat sini. Nisa tu satu lagi. If you have internet problem or limited mobile data, you don't have to attend the full class. Okay, I will be recording. I will upload the recording in the YouTube, so you can leave lah after whenever you think you have to. So tak ada paksaan. Okay. Ada ke siapa-siapa yang ada internet problem? Tak ada. Banyak biasanya tak ada kan. Okay, so saya nak share screen. Kat mana? Try again. Okay. Okay. So can you see my slide?
Yes, madam.
Okay.
Yes.
Where did we stop last time? I think we stop here lah, lebih kurang, right? So we talk about, then I talk about carriers, different type of carriers in semiconductor. You have what do you call it, electron and holes. Basically, it's there are two, like we imagine it like a particle that carry charge. So when the hole or electron move in one direction, if it moves randomly, you don't have current. But if move in one direction, there's a flow of charge, then you have current. Okay, so if the carriers are moving, but moving in random, so there's no like one direction, there won't be any current. You won't get any current. Okay, so okay, so now, so this is the predict table. If you look at the predict table, okay. So normally semiconductor material are in this group. Kat sini. So group 3, group 4, group 5. Okay, so silicon that normally you see, silicon is in group 4. So you have 4 outer electrons. So but as mentioned, the semiconductor material can be from group 4, normally silicon yang paling famous, and others normally in group 3, 5. For example, gallium arsenide. Buat dia besar sikit. So gallium arsenide, that's one type of semiconductor. You can have silicon germanium. It's a combination. So there are two types of semiconductor. One we call it elemental, and the other one is we call it compound. Okay, so elemental means like a single element. For example, silicon is an elemental semiconductor. Compound is for example gallium arsenide. Is a combination of gallium and also arsenide. It's a compound semiconductor. Silicon germanium is a compound semiconductor. You can also have gallium, aluminium, phosphide, 3 elements in one semiconductor. So the criteria to be a semiconductor is that it's in between metal and insulator, right? We learned last time. So you can control, you can dope it, and you can control the conductivity of the material. So that's a semiconductor, basically. So most of it will revolve in these three groups. Okay. If you have any question, just stop me anytime. Okay.
Yeah, madam.
Yes.
My name is Afika. Actually, I was in quarantine right now, so the line in my room is not very good. It keeps connecting and cut off. So can I watch the recording later?
Okay. So where do you stay, Afika?
I'm staying at home, but I'm in my room quarantining myself. So this side of the house, I mean in my room, the line is very poor, so it keeps cut off and reconnecting.
Okay, no problem. You can later watch in the video.
Okay, thank you so much.
But you put your name in the attendance, right?
Yeah, I already put my name in the attendance.
Okay, Afika.
Okay, thank you, madam.
Okay. Okay, these are just to show you the predictable elements in pictures. What it can, what each element. So Allah created all the elements in this world. So this is amazing. If you look at it, each single one has a very important. My daughter is trying to communicate. Okay, so every single material has a important role in this world. Every single, even in you have the transition material, you have the super heavy element which people have discovered, and each one has a role to play. Okay, and we today we are in our course we just concentrate just on the semiconductor. Okay, now materials. So we talk about conductors. Metal are conductors. It has low resistance that allows current. Insulator have high resistance which suppresses the electrical current. And semiconductor is in between, as mentioned before. And if you look here, here's the resistivity and conductivity of selected material at room temperature. The resistivity and conductivity of a material will change with temperature. Okay, especially semiconductor. Semiconductor is very sensitive to temperature. So we'll talk about the physics after that, after this inshallah. So you can see here, this is the semiconductor. And if you look at the resistivity is in between the metal and also the insulator. Wait a second. Okay, sorry for that. So this is a graph of a band gap versus lattice constant. Before that, let me ask you, what is a band gap? Anybody? What is a band gap? Anybody can help to answer? What is the band gap? You learn this in first year. Nobody knows? You want me to call your names? Siti Farhana. Why can't I see your face?
Sorry, madam.
That camera tu you kena turunkan sikit.
Okay.
Yang lain siapa nak jawab? What is the band gap? Nobody remembers. Kita tak ingat band gap ni macam mana kita nak belajar semiconductor ni. Mirza Ashraf.
The difference in energy.
Is what?
Distance between the electron.
Distance between electron.
Electron and the conduction.
Electron conduction what?
Conduction band.
What is conduction band?
Tahu kan?
Apa nak tolong? Okay, it's okay. If you don't know, you can just say your friend can help you. I'm sure many. So Akmal, welcome. Why are you late? Akmal, can you hear me? You cannot hear me, Akmal? Can you hear me or not?
Yes, madam.
Akmam, can you hear me or no? I don't know.
Yes,
You
yes.
put your name there, Akmam. Is that your real name? Okay. Right. So, what's a band gap? What is conduction band? Ni basic lah. Dia kalau ikut dia macam fardu ain sebelum masuk fardu kifayah. Fardu ain tu kita kena settle dulu fardu ain. Kalau tak kita boleh nak pergi yang advance lah. So, Muhaimin, what is band gap?
In order to break the covalent bond, the valence electron must get a minimum energy.
So, in your own words, what is the band gap?
Minimum energy to break the covalent bond of the apa benda lah tu.
Energy. So, that is band gap energy. Okay. So, that is band gap energy. What is band gap? Haris?
It's the distance from the outer electrons from the middle of the element.
What? The distance between what?
The distance of the outer electrons from the outer layer of the element.
Okay. Right. Okay, let me explain lah. Kalau saya tak explain ni, takut awak semua salah faham ajaran sesat ke apa ke. So, I better explain properly. So, this will take time. So, sebenarnya, to be honest with you, this shouldn't be in the semiconductor device. This should be in first year. So, I shouldn't have to repeat myself. Tapi because I have to repeat, so it will take more time. Itu masalahnya. In the end, kita tak habis syllabus kita. Tapi because if you don't understand, we cannot proceed. Okay, so remember we have in a material, how many atoms you have in a material? Anybody can tell me how many atoms you have in a material? Give me a guess. 1, 10, 20, 1 million, 10 billion? No idea. Macam mana ni no idea? Awak dah nak grad dah. Dah third year, fourth year. Munira? How many guess in a material? How many atoms you have?
Maybe 10.
10. Okay, thank you for the guess. Ni Aizuddin?
One.
One? MasyaAllah. Okay, thank you, brother. Anas?
I don't know, maybe 2, maybe?
2. Saya kena stop lah. Saya nak tengok muka awak, brothers and sisters. Macam mana kita ni? I'm so worried. Kita kena ada common sense, okay? You learn this in SPM already. So, for example, in a piece of material, even if this big or even smaller, very small, even like 1 cm by 1 cm or 1 milliliter by 1 millimeter or 1 cubic meter, 1 centimeter by 1 centimeter by 1 centimeter, there are millions of atoms. Millions. Atoms. You know how many atoms in your body? You cannot count it. It's too many. Ni atom. So when you answer 1 or 2, it doesn't make sense at all. So in a material, there are like millions, billions of atoms. Okay. So that is So we are dealing with a material which have a lot of atoms. So and these atoms are all created by Allah, and each single one has a purpose to play. So it's very complicated. Even it's a small semiconductor, any material, they have a lot of atoms. Okay, so let me share again. Okay, so if so, you need to imagine a semiconductor material with millions of atoms. But here I will draw just a few because I cannot draw millions. If I start drawing millions, we will not finish the class. Okay, so this is representative. There are a lot. So each one have its own energy state, right? Remember? So this is for each one. So the one that you normally draw for an atom, that's one atom. But it's like you have many millions of it. Okay. So when you have many crammed into a small area, what happens is this energy level, ni nama dia energy level lah. Ni yang bulat-bulat ni, yang ada elektron kat sini ni. You have electron there called energy levels, and this energy level will interact sebab dia akan overlap. Ni pun dia akan overlap with each other. Okay, when the energy level starts to overlap, okay, they will what do you call it, interact, and they will apa nama tu, dia akan jadi macam they will become energy state. They become and each of the energy level here, you can imagine millions, right? Each of the energy level cannot it cannot be on top of each other. It has to be discrete. So the word is discrete. Discrete. Okay. But when you have millions, can you imagine millions of lines and very close to each other? So it becomes a band. It becomes a band. So, and you can go and Google and read about Pauli exclusion principle. So go and read about Pauli exclusion principle. It will tell you how in the end we get the band. So because of the many of the atoms energy level interacting with each other, so we're going to have a band. So to simplify, we engineers, we like to simplify, right? So if we simplify, we make it into two bands. So actually, to be exact, we have to draw it like this. Two band. This is called the conduction band. And this is called the valence band. And the one that your friend was answering just now, the distance between the energy, so the y-axis here is energy. Okay, the difference between the valence band and conduction band is called the energy band gap, EG. Okay, so now, so if you look at the lines over here, there are inner what do you call inner energy level and outer energy level, right? And if you remember in periodic table, the outer energy levels are the one that active. Remember? Kita ingat langsung lah. Ingat kan? Kita kena positif. Ingat. So the in the periodic table, when we say group 4, it means that 4 outer electrons. The electrons are outside, right? The electrons are outside here. 1, 2, 3, 4. 1, 2, 3, 4. If it's group 4, it's 4 outer electrons. So these 4 outer electrons, if gain enough energy, it can be in the conduction band. So in conduction band, actually you have millions of energy level like this, very close together. Ni macam when it's very close together, it's just like one thing. So the electron can just, if you have an electron here, the electron can go to another level, can go to another level. you need to imagine energy level ni macam a place to sit. If there's no energy level, the electron cannot exist there. There must be an energy level for electron to what do you call it? For electron to be to
Excite.
Huh?
Excite kan?
Tak dengar.
Excite.
Excite,
Excitation.
no, bukan excite. Excite tu another what do you call it? Another mechanism. Ni energy level just to be there so that the electron can stay. If you don't have energy level, the electron cannot exist there. Okay. So when you have a lot of because of this Pauli exclusion principle, you have this, then you will have two separate bands. We'll call it conduction band and valence band. Valence band pun sama. You have a lot of energy level. The difference is, okay, what's the difference between conduction band and valence band? The valence band are full of bound electrons. Remember in the first class when I say bound electron, what does it mean? Kita cover kan? Bound electron, free electron. Kita tak? Please answer me. Hello?
Yes, madam.
Huh?
Yes.
Yes. Okay, so what is bound electron? Azian?
Bound electron is the one that cannot move freely.
I cannot hear you. Kuat sikit boleh?
Cannot move freely.
Yes. So it cannot move. Basically, it cannot move. Cannot move freely means cannot move. So electrons here, they are like millions for each atom. So the one inside, that inside in the energy level ni ada electron kan full, tapi dia tak boleh move. So it's and all this the one that cannot move are in the valence band. So you have a lot of electrons, but it cannot move. So when electron cannot move, it doesn't mean it's not important to us. It's not beneficial because it's doing nothing. Okay. And as I mentioned before, Allah created everything in pairs. So we have electron, we have holes. So the same in the conduction band, full of bound holes. Okay, the opposite. They do the opposite. So here that you have a lot of holes, but it's actually bound, cannot move. Good. So normally we don't talk about that. Tapi I'm just telling you so that you understand later. Macam mana boleh excite? Macam mana elektron tu boleh pergi? Because starting there are a lot of electrons here, but the electrons cannot move, and there are lots of holes there, but the hole cannot move. Okay. So how do we get current? What's the condition to get current? So the condition to get current is to remove this. So the condition to get current is for electron or hole to move. Okay, remember when I said what is current? Current is a net flow of carriers. So it's either electron or hole. So let's talk about electron. So when the electron here are bound, right? In order for it to free, it need to go to the conduction band, because in conduction band there are lots of empty state. There's lots of empty energy state, so the electron can move. You can imagine, I remember my lecturer in UK told me, you can imagine like a room. If we are all in a room, right? A room and full of people. Can we move or no? Cannot, right? So the same goes here. In the valence band, there are lots of electrons but cannot move because no space. But then if there's an empty space, we have an empty space then in the room, then then we can start to move. It's the same concept here. In the conduction band, there are lots of empty space. So the electron first need to go to the conduction band to go to the empty energy state. So when it's there, And this is a band, right? When we say a band, it's like the whole, the electron now can move here, move there, move anywhere, because there are lots of empty energy state. So number one, for us to get current, very important, we need free electron. And how do we get free electron? We need to get the electron to be in the conduction band. Okay, with many ways. One of the ways here that I told you is the word is excite. Sometimes you read book, they use the word excite. Sometimes they use the word jump. So the electron will be excited or jump into the conduction band. So remember, holes are the opposite of what do you call it, electron. So let's draw the hole. Okay, so we have hole here. Hole here cannot move. Whenever hole in conduction band, it cannot move. So in order for it to become to move freely, it needs to go to the valence band. So we also need to excite the electron, the hole from the conduction band to the valence band. So when the hole are here, again the hole can move everywhere. Okay. My question is, now when we have electron move freely over here and hole move freely over here and hole move freely over here, do we have current now? Do we have current? Yes or no?
Not yet, so
Anas?
I think not. I think no.
No. Why?
Because it is only flowing in the same place.
Yes, because it's flowing. No, it's not. It's moving, but it's moving randomly. So this electron will move, go there, go here, go. There's no net flow. The same as hole over here. The hole will move here, move there, but there's no net flow. So we need to put a potential or a voltage across the semiconductor material for us to see some current. Okay, sebab tu if you take a piece of semiconductor like this, for example, we take a semiconductor like this, there's no current, kita tak akan kena electric charge because there are electron holes moving freely, but it's moving randomly. Okay. Now, there are a few ways that we can have we can have this free electron and free holes. Number one, for excitation. Normally you can get it through with temperature or heat. So at room temperature, now we are in room temperature, right? Room temperature has heat, and this heat is enough. It depends on the semiconductor and the band gap. Okay, the band gap energy here is very important because some material have this band gap. Some materials have this band gap. So it depends on so this DC. So this is EG1. So depending on different materials, it has different band gap. I always tell my students, this band gap is like your thumbprint. For human, right? If you want to differentiate between Anas and Zarif, we don't look at the face, we can just look at the thumbprint because it's very unique, right? So similarly, semiconductor have its own thumbprint, and the thumbprint of a semiconductor is the band gap energy. Okay, so different semiconductor have different band gap energy and other things to differentiate them. So for example, if this is for example this is 3.2 eV. The unit for the band gap is energy, but we change it to eV because the number is very small. So electron volt, when we change to electron volt, we get a good number. Otherwise, it will be 10 to power or minus 20 something. So the number is too big. So that's why we change it to EV, electron volts. So maybe this one is 0.5 EV, this one is 1.1 EV. Okay, so here are three different semiconductor material, say A, B, and C, and it has different band gap energy. And what happens is it will react differently with the temperature. How? Remember last time we said in order for us to get free carrier or free electron, the electron need to go from valence band to conduction band. So here the same. So we have a electron here need to go over here. Need to go to here. Okay, tell me A, B, or C. Which one is the easiest for the electrons to jump? A, B, or C?
B.
B.
B? Zarif, you agree?
Yes, madam. BB.
Good. So B, why B?
Because it's the smallest.
Yeah, so for example kita pun, we human beings, we want to jump this big or this big, right? So we will always, the easiest to jump the smaller distance. So the same as electron over here. So you can see, for example, at, let's say at 300 Kelvin, 300 Kelvin is room temperature. So since B has the smallest energy to overcome, so you will see a lot more of electron be able to go here. So this one may be one. So let me see. I'm just doing this to show comparison. So maybe 5, this only 1, maybe this one 2. So at the same room temperature, device B will have more free carriers compared to device C and A. Okay, so it's very dependent on the energy band gap. Okay, so the smaller the energy the band gap energy, the more sensitive it is to temperature. Okay, who knows what's the band gap of silicon? Who knows? Google sekejap je dapat. It's 1.1 EV. Okay, so it's not too small, it's not too big. It's macam medium jugalah, right? So it's not that sensitive to temperature. But if you increase the temperature, it will affect. That's why you cannot use your electronic devices they will have clocks. It has a certain temperature range to work. Any question? Soalan?
No.
Everybody understand? Semua faham ke? Kau faham saya tanya soalan ni? Asal awak tak ada soalan? So that's why I say maybe kelas lain lagi senang, tak payah bercakap dalam kelas.
InsyaAllah faham.
Ha?
InsyaAllah faham.
InsyaAllah faham. Ha? Okay, since semua senyap dan faham ni, saya nak tanya soalan. Afiq, what is the conduction band?
What is the conduction band? It's a where it's a band with full of bound holes, and yeah.
And
it's a conduction. No, tak ada end.
So kenapa nama dia conduction?
Because if we are at the conduction band, then which means it has a way that would give the way that freely.
Putus. Why is it called conduction band? Faris, Amirul Faris.
Okay. Why it is called conduction band? Actually, conduction band is a band of electron that it's a band of electron can jump in order to move freely.
Okay, the name conduction band because it refers to electron. For when free electrons are in the band, it can conduct electricity. So although there's electron hole, right? So but they use the name conduction band to refer more to the electron. So for electron to move, it has to be in the conduction band. So therefore, there's conduction of electricity. For holes to move, it has to be in the valence band. Okay, that's the most important thing if you have to remember. And also remember how we that the electron need to be excited, need to be need to be pushed or like excited from the valence to conduction and holes from conduction to valence band. Okay, good. Pukul apa kita habis kelas ni?
11.20.
9:20. Right. So let's see our what do you call it? Like sebab saya tadi tu cerita we were looking at the as I mentioned, anytime if you have internet problem you want to leave, just let me know and then you can leave. Ada paksaan. La ikrah fiddin. Kenapa tak boleh? Alright, so that's why we go to band gap. So as I said, band gap tu macam relation je, the one that I just told you just now. Tak masuk lagi the real semiconductor device punya subject. Okay, so we have band gap. You know what's a band gap now, right? And then lattice constant. You know what's a lattice constant? Ni pun basic juga. Anybody? I give you 30 seconds. Google what is a lattice constant. And then let me know. 30 seconds ya. Type 2 second. Baca 10 second. Beritahu saya. Okay, who can answer me what is a lattice constant? Volunteer lah sebelum saya panggil nama. Siapa yang tak bersuara lagi ni? Mirza Azhar. What is lattice constant?
Is the side length of the cube?
Dengar?
Is the side length of the cube?
Side line.
Side length.
Side line tu apa?
Like physical dimension of unit cells in a crystal lattice.
Okay, in your own words, what is a lattice constant?
Maybe a dimension of a cube.
It doesn't have to be a cube. Again, try. Physical dimension of what?
Particle.
What is a lattice? Okay, sekarang ni kita undur belakang satu step. Go and Google lattice. What is a lattice? If you don't understand lattice, you can answer lattice constant. Okay, give you 30 seconds, Google lattice. Paling senang Wikipedia. Kadang in FIP you cannot use Wikipedia, but to understand things, Wikipedia is the easiest, if you ask me. Okay, Ikmal, what is lattice?
Distance between molecule or atoms. Distance between molecule or atoms.
Tu lattice constant. Right? Lattice saja. Google lain pula. Kenapa Muhaimin dah tak nampak muka? Ke saya je tak nampak? Haris. Haris. What is a lattice?
Lattice is a structure that's made up of many similar structures.
Okay, faham ke Munirah? Kalau faham, saya akan tanya awak lagi. Awak faham ke? Munirah?
Faham juga kot. Ada sama dengan apa yang saya faham.
Okay, apa? Can you explain what is lattice, Munirah?
Lattice tu macam susunan dalam atom ataupun macam yang Biza kata dia macam cube kan. So dia macam susunan untuk bentuk pattern of atom or nucleus ion in the structure.
Okay, good. Everybody understand lattice, right? So basically lattice is just arrangement of atoms inside a material. So it can be cubic, it can be diamond structure. It depends on the material, how the atoms are connected and arranged. Okay, so that is a lattice. Lattice constant, as mentioned by brother just now. Mana yang jawab tadi yang saya kata Iqmal lah. The lattice constant is the distance between two atoms inside the lattice. So because lattice is the arrangement of the atoms. So lattice constant is the distance between distance ni dalam bentuk meter lah. Unit dia meter sebab distance in terms in the lattice. Okay, that's a lattice constant. So okay. So sekarang ni kita tengok kat sini kan. Tengok kat sini. So now, right? So kat mana saya tengok? Oh, kat sini. Alright. So lattice constant is the, for example, if you have a atom macam ni kan. Saya tengah draw atom yang tak cantik ni. Okay, the distance between atom to atom here. Normally the symbol is A. Can you see? Nampak? Nampak tak saya lukis?
Yes, madam.
Nampak.
Normally lattice constant are denoted as A. And this A is the distance between atom to atom. Okay, and it's very important. As I mentioned, kita punya badan kita, our body, one of the thumb to differentiate between one person to another person is the thumbprint. Thumbprint. So the thumbprint for semiconductor material, number one is the band gap energy. Number two is the lattice constant. Macam kita kan sekarang ni orang boleh scan mata. Pernah tak tengok orang dulu kan orang selalu kena thumbprint ni. Sekarang ni orang boleh scan mata. Just looking at your eyes, they can know who you are. So another like what they call it parameters that differentiate between one semiconductor material to another is the lattice constant. Different materials have different lattice constant. So if you look in this graph here, this is a graph of band gap energy versus lattice constant. And the unit is Armstrong. You know what's Armstrong? Armstrong is equals to, nak tulis pula. So Armstrong equals to 1 times 10 to power minus 10 meter. So it's very small. So normally if you look here, when it say 3.6, 5.1, that is 3.6 times 10 to the power minus 10 meter. Okay, so that's the distance between atom to atom. Okay, in a semiconductor. So this is a graph of lattice constant versus band gap, and actually this graph is very comprehensive. It's also have different colors. Different colors. For this is group 4 materials. We can see the green one is group 4. Not green one, but the red one, sorry. The red one is group 4. So you can silicon is group 4, germanium is group 4. So these are elemental semiconductor. And you have also semiconductor of 3, 5 material, a combination compound material combining group 3 and group 5. So is the pink here, which is gallium arsenide, indium phosphide, aluminum nitride, and also you have group 2, 4. Okay, good. So with 2, 5. Ini nombor berapa ni? 5, right? Okay. So yang biasa normal that we use is this and this. Okay. So right. So I want you, this is normal to have in the exam, this graph. I'm just telling you, this is my favorite graph. So normally I won't tell everything about the graph. You should look at the graph and study it and understand what is it telling you. So this line, you can see some lines, right? This line is showing macam mana? It's showing how we can modify the material to become another material. For example, yang ni, we have aluminum nitride here and then gallium nitride. So we can actually play with the percentage of nitride here. You can make it aluminium gallium nitride. Aluminium gallium nitride is a semiconductor. So we can play around. As an engineer, our job to design, right? So our job is to design devices. And to design devices, we need to understand the material. Otherwise, we need to know each material can do what. And if you can see aluminum nitride, the band gap is roughly 6.3. The gallium nitride is roughly 3.7. So yeah, here. So if you want as a engineer, sometimes you want a material with a band gap of 4.5. If you look here, there's nothing on 4.5 in this region. So therefore, we need to play around. We need to play around with the material inside. If we play with the percentage of nitride in aluminum gallium nitride, you can get 4.5. So I'm just telling you, as an engineer, we can engineer the material to become the band gap that we want. And because band gap will give you the performance of the device. Okay, and we'll also what do you call it? Will also give you the robustness of the device with certain condition, temperature ke, radiation ke. So we can play around with the band gap. Faham tak? Okay ke? Semua okay ke? Tak payah nak terima. Faham ah? Okay, basically that's so saya tak masuk lagi on the direct band gap and indirect band gap material. Yang itu nanti saya akan masuk later. Okay, now let's go for next slide. Okay, ini senang. Perlu saya nak mengaji cerita awak benda ni so that you understand. You know, as I mentioned, the konsep dalam semiconductor ni bukan senang. Sebab dia tak nampak. Kalau benda nampak senang, mechanical, sorry lah, bukan nak kata orang mechanical one of the easiest sebab dia what you call it, nampak semua benda. Physics dia susah juga. Tapi semiconductor lagi payah sebab you don't see. Can you see electron? Tak nampak. Nak kena imagine energy band diagram lagi pula. Lepas tu band gap lagi. So you need to understand and imagine in your head. That's why I'm drawing. When you draw, you can imagine it, insyaAllah. Okay, so ada soalan ke? Kalau ada soalan, tanyalah sambil-sambil saya mengajar ni. Ada ke? Ada, semua faham. Bagus lah semuanya. Kita tengok nanti kuis lah. Kalau boleh jawab kuis tu, faham lah tu insyaAllah. Kalau tak boleh tu, something not right. Okay. So, we introduce conduction and balance band and band gap. So, as I mentioned, at 0 Kelvin, okay, my question to you, at 0 Kelvin, is there any free electron or free hole? Siapa nak tolong jawab?
What was the question again, madam?
My question, at 0 Kelvin, temperature 0 Kelvin, is there any free electron or free hole?
According to the slide, no, because it said that balance band is filled and the conduction band is empty.
Why?
Because there is not enough heat to excite the electrons.
Yes, 0 Kelvin, there's no heat at all. Actually, in life, nobody has never ever, we can never ever in real life make experiment at 0 Kelvin. The closest they can go to 0.001 Kelvin, right? It's very small Kelvin. But because when 0 Kelvin, everything stopped. Everything stopped functioning because nothing moves, right? And so at 0 Kelvin, theoretically, from theory, we know we shouldn't have any free electrons because there's no energy. How the electron can go there? So also no hole, no free hole because there's no energy. Okay, so at 0 Kelvin, nothing happens. Okay. Now, and to even go to 0.0001 Kelvin is crazy, expensive, and difficult. Hebatnya Allah. Allah can do anything. Allah can do at 0 Kelvin if Allah wants. So there's one I've been reading about the hellfire and Jannah. In hellfire, there are torches of the fire, panasan. But there also some books also talk about the torture is very cold. Too cold also a torture. If you've been in a negara sejuk, too cold also you have frostbite. You will lose your hand, you have numbness, sakit ni yang sejuk sangat. So that's also a torture from Allah. Okay, now interesting facts. You can read on your own. I already give this to you. Bacalah sendiri. Electron conduction, hole conduction. Okay. Now intrinsic and extrinsic. Belajar dah. You learn this in your first year. Who can tell me what's intrinsic semiconductor and what's extrinsic? What is intrinsic semiconductor and what is extrinsic semiconductor? Azimuddin, can you help me?
Intrinsic semiconductor, I think is pure semiconductor.
Pure.
Pure.
Extrinsic, not pure.
Extrinsic, it combined with other elements.
So gallium arsenide, is it intrinsic or extrinsic?
Extrinsic.
Do you agree, Muhammad Anas?
I don't remember, madam.
Don't remember. Hilang ingatan. Kita tanya orang lain lah pula. Muhaimin. Do you agree with Azimuddin?
He said extrinsic.
Dia kata, saya tanya gallium arsenide, is it intrinsic ke extrinsic? Dia jawab extrinsic. Betul ke tak?
Intrinsic.
So you say tak betul lah. So what is extrinsic semiconductor?
Extrinsic kita campur impurities.
Okay, what kind of impurities?
Selain pada semiconductor gitu.
Selain daripada semiconductor. Why do you want to add impurities?
Sebab kita nak main-mainkan dengan dia punya band gap semua benda lah, dia punya properties tu.
Oh, kita nak main dengan band gap dia. Tapi kalau main band gap dia jadi semiconductor material lain.
Tak, kita nak main dengan conductivity dia sebenarnya.
Sebenarnya conductivity. Okay. So,
Ha.
alright. Betul. So brothers, selalu saya saja tanya soalan ni because normally student get confused between intrinsic, extrinsic, elemental semiconductor and compound semiconductor. Remember I just talked about the two just now. So what are the difference? So semiconductor ni can be categorized in elemental and compound. Can also be categorized as extrinsic dengan intrinsic. So yang elemental ke compound je is just showing even is the elemental semiconductor can also be intrinsic, can also be extrinsic. The compound semiconductor can also be intrinsic or extrinsic. Okay, so sebab why intrinsic semiconductor, when you mention pure means that you don't add any impurities. No, so no impurities. Okay, extrinsic semiconductor you have impurities. For example, impurities you put is doping. Okay, you add doping and it's called impurities because that's not the element of the semiconductor material. That doesn't change the band gap. Whenever you add a material that change the band gap, it becomes another semiconductor material. So dia bukan dia jadi intrinsic extrinsic, dia jadi it becomes another compound semiconductor.
Madam.
When you say yes,
Madam.
Yeah.
So kiranya gallium arsenide tu compound lah.
Gallium arsenide is a compound semiconductor. It can be
compound semiconductor and intrinsic semiconductor.
It can be intrinsic, it can be extrinsic. It depends. If I doping,
depends. If doping with impurities, it becomes extrinsic. But if we use gallium arsenide only, it is intrinsic.
Yes.
Okay.
Okay, so this is the normal common misconception student lah. Bila tanya soalan ni mesti salah, mesti ada salah. So now you understand, right? So dia maknanya gallium arsenide can be intrinsic. Indium gallium arsenide dia ada kan, indium gallium arsenide also semiconductor can be intrinsic. Aluminium gallium phosphide also semiconductor material, it can be intrinsic. If you dope it, then become extrinsic. Okay, so kita masuk balik. Share screen. Kalau ada satu button untuk share screen kan. Dah lah kena. Saya rasa tak faham kenapa bila share dia hitam. Buat sekali lagi. Tapi Alhamdulillah, at least I can share directly through my iPad. Teruk kita susah nak mengajar. Okay, so you know what's intrinsic, what extrinsic? So intrinsic semiconductor, the characteristic of intrinsic semiconductor is that the number of electrons is the same as the number of holes. Why? Masa first year dulu, electronic you hafal je lah, intrinsic semiconductor, the number of electrons equals the number of holes. Now in this course, you're supposed to understand why. The answer of why is, remember we talk about excitation. Electron need to be excited to go for it to be there, and hole to be free. So hole need to be excited to the valence band to be free. Okay, so and remember electron hole need is always the opposite, equal and opposite. So maknanya every time an electron excited to go to the conduction band across the band gap ni, across the band gap, a hole will also be excited to the valence band. So sebab saya dibagi, normally if you read book they will say electron hole pairs. It's always in pairs. So if you excite one electron here, one hole definitely will go down. Macam tu. So that's why the number of electron hole inside an intrinsic semiconductor is the same. So for example 300 Kelvin, this amount, for example, five electrons being excited, 5 holes will also be excited. Okay, so that's why in intrinsic semiconductor, and in intrinsic semiconductor, the electron needs to overcome this band gap. So kalau band gap dia besar, it means that susahlah dia. So you have lower number of electron hole. Okay, if the band gap is bigger, because it requires more energy at the same temperature. Now, there's a mathematics here, but you can read it. Biasanya saya tak go through mathematics lah. As I mentioned dalam kelas ni, saya lebih kepada understanding. Soalan saya pun tak ada math sangat. Okay. Right, so now, so this, can you imagine, so the same energy band here, the number of electrons or holes, free electron and holes, will depend on the temperature. Very dependent on temperature. Let's say T equals to 300K. Okay, saya bagi 3 example. T equals 0 Kelvin, T equals to 300 Kelvin, and T equals to 500 Kelvin. So naturally, at higher temperature, you have more free electrons or free holes because the electrons here have more energy to go at 500 Kelvin. So the higher the temperature, the more free carriers you have. So semiconductor is very dependent on temperature. If metal, metal, if I ask you to draw the energy band diagram of metal, how does it look like? Kalau metal dia punya yang merah ni conduction band, yang hitam ni valence band. The conduction and valence band overlap each other. So that's why metal dia tak ada masalah with temperature. It will be the same conductivity roughly, even if we increase or decrease the temperature. Tapi semiconductor dia sensitive. So when we design, we need to look carefully at the temperature because it will affect of how many free carriers. Okay, the temperature will affect the free carriers. And kalau later, if you learn transistors, it will affect the gain. Okay, the gain of the material, of the device, sorry. So, and that then, if it affects the number of free carriers, it means that it will affect the carrier concentration. What is carrier concentration? Anybody can help me? What is carrier concentration? Awak dah belajar electronics, I'm sure awak dah fourth year, mesti awak tahu dah kan, takkan? Concentration. What is what is carrier concentration? Sebelum kita end the class. Kelas ni ada, okay. Azian boleh bantu saya. What is carrier concentration? Nothing stops you to Google lah. You can always Google.
Of electron, the number of electron in conduction band, ataupun the number of holes in valence band.
What's the unit of
the
carrier
number
concentration?
of electron.
What's the unit of carrier concentration?
Apa dia?
Apa unit dia, unit?
SI unit, density.
Density. So, what is carrier concentration? Normally, if you want to answer what is it, you look at the unit.
Meter.
Dengar lah je.
Meter. Kawan saya masalah nak
Tak apa. Afiq,
speaker
what is,
problem.
Afiq, can you help with what is carrier concentration? Afiq. Muhammad Afiq.
Carrier concentration is how to say this? Carrier charge density.
Huh?
Carrier charge density. So basically,
Basically,
what it do is that it's it's like if how much free carriers are there if we introduce thermal excitation from valence bands to conduction band. So
complicated. You were there, tapi a bit complicated lah. Sebenarnya simple je. Carrier concentration is number of free carriers per unit unit volume. So that's why the unit for carrier concentration is per centimeter cube. So actually per density. How many numbers of free carriers per unit volume? Volume is area times the height, right? So that's all. So carrier concentration is important because I can say I have 10 million, but okay, I have a 10 electron, but the area or the volume is like apa nama ni, millions of meters, besar sangat, tapi ada 10 je, sikit lah. Tapi I have like 10 but in a very small area, the density is high. So that's why in semiconductor normally we talk about carrier density or carrier concentration. Nama dia kadang carrier density or carrier concentration, and that is number of free carriers per unit volume. And we'll continue from there inshallah in next class. Okay, so I think that's enough for today. Hopefully you understand. Kalau ada soalan, we can discuss in next class. Normally in this class kan, we will always close with the doa. So we need a brother to close the class before we can end. Because brothers are the leaders of the ummah, and you have to rotate every time. Hari ni orang lain. Okay, so siapa nak volunteer? Kalau kita tak boleh keluar ni, saya semua nak berehat, I'm sure. Hari tu siapa? Hari tu ada orang baca doa tak? Siapa baca itu? Munirah? Ingat?
Saya hari tu.
Itu Afiq. So thank you Afiq. So Afiq has done his responsibility. The rest of you. Apa? Nak jadi ketua keluarga kan, nak kahwin lepas ni, nak jadi imam. Ni nak boleh baca doa. Betul tak? Okay, siapa? Kalau saya nak ambil menantu pun tak boleh baca doa, macam mana ni?
Ya, ada.
Aizudin ke? Okay, silakan. Bismillah.
Bismillahirrahmanirrahim. Subhanakallahumma wa bihamdika asyhadu an la ilaha illa anta astaghfiruka wa atubu ilaik. Bismillahirrahmanirrahim. Wal 'ashr innal insana lafi khusr illa alladzina amanu wa amilus solihat wa tawassaw bil haqqi wa tawassaw bis sabr.
I want a doa. Aizudin.
Bismillahirrahmanirrahim. Alhamdulillah rabbil alamin. Wassalatu wassalamu ala sayyidil mursalin wa ala alihi wa ashabihi ajma'in. Allahumma ighfir lana dhunubana wal walidayna warhamhuma kama rabbayani shaghira. Allahumma inna nas'aluka ridhaka wal jannah wa na'udzu bika min sakhatika wan nar. Allahumma innaka 'afuwwun karim tuhibbul 'afwa fa'fu 'anna wa walidina wal jami'il mu'minina wal mu'minat wal muslimina wal muslimat bi rahmatika ya arhamar rahimin. Rabbi yassir wa la tu'assir ya karim. Rabbi tammi bil khair. Rabbana atina fid dunya hasanah wa fil akhirati hasanah wa qina adzaban nar. Wa sallallahu ala sayyidina Muhammad wa ala alihi wa sahbihi wasallam. Walhamdulillahi rabbil alamin.
Alhamdulillah Rabbil Alamin. Okay, thank you very much. Let's close with tasbih kifarah. Subhanakallahumma bihamdika asyhadu an la ilaha illa anta astaghfiruka wa atubu ilaik. Okay, assalamualaikum warahmatullahi wabarakatuh.